All right, so abandoning the calculator, we were on example D, right? Example 9D. And once we wrote it as a geometric series with a rule of sequence of 10/11, we knew it converged. And now we know to what it converges. It converges to the first term, which is going to be what? It's 1 over 1.1 squared. Or you could say, in this case, it's 10/11 squared. I like that version better because 10/11 squared is 100 over 121st, square the top and bottom, all over 1 minus r. What was our r? 10/11. And then, of course, you could simplify that. That's 100 over 121, and that's going to give you 11/11 minus 10, which is 1/11. So dividing by 1/11 is the same as multiplying by 11 over 1, which simplifies to 100 over 11. Divides out. So the geometric series, the infinite geometric series, when it converges, it will converge to a number that we can compute. And these make good non-calculator multiple choice questions, all right? And it's one of the few that we can actually find the sum of. Another type of series, which is not on the BC exam, but I still like to cover it because it's pretty cool. It's called a telescoping series. And Micah, this is the one that showed up on the UIL math test, which was interesting. A telescoping series is called telescoping because when you expand it out, it's an infinitely long telescope. When you start expanding out the terms, they'll look something like this: 1 minus a half, plus a half minus a third, plus a third minus a fourth, plus a fourth minus a fifth. If you expand out a sufficient number of terms, you will see some neat things collapsing all the way down the line. For instance, this 1/2 will cancel with that 1/2. This 1/3 will cancel with that 1/3. This 1/4 will cancel with that 1/4. This 1/5 will cancel with that 1/5. All the way down the line, they go to 0, and we're just left with anything that doesn't cancel. So there will always be a few residual terms, and then after which everything else will cancel. It's not always just the first term. You might have 1 or 2 or 3 residual terms, but after a certain point, everything else down the line will cancel. So in this case, what's left? 1. So the sum of this infinite series is 1. Okay, so how do we spot a telescoping series? Well, if we spot it, we can use what's called a telescoping series test, which we can find the sum of to determine if it converges. So here's one. The sum from 1 to infinity of 1 over 2n plus 1 minus 1 over 2n minus 3. So let's first do the nth term test for divergence. We'll do that. Now you could take the series of each term individually, like you would the integral. What happens to 1 over 2n plus 1 as n goes to infinity? It goes to 0. So that series has a chance at converging. 1 over 2n plus 3 also goes to 0, so that series has a chance of converging. In this case, if you're not sure, you could get a common denominator, but I'm going to go ahead and start expanding out the terms. So if I plug in a 1, what do we get? We get 1 over 3 minus 1 over 5. Plus, when I plug in a 2, I get 1 over 5 minus 1 over 7. Plus, when I plug in a 3, I get 1 over 7 minus 1 over 9. Plus, dot, dot, dot. Now, if you start looking at the pattern here, you have a negative 1/5 and a positive 1/5. You have a negative 1/7 and a positive 1/7. You're going to have a negative 1/9, and then guess what the next one will be? Positive 1/9. So these will cancel out all the way down the line, and the only term that you're left with is a third. So this series, infinite series, actually converges. And it converges to what? 1/3. So aside from the geometric series, this is really the only other one that we can find the actual sum of for a good while until we learn power series. Okay? Converges. What about this one? Let's do the nth term test for divergence. This is really like 1 over n squared plus n. What happens to 1 over n squared as n goes to infinity? It goes to 0, right? It goes to 0. So this thing has a chance at converging. What would your intuition tell you? The nth term test just says has a chance. It doesn't say it converges. But if it grows similar to 1 over n squared, and we saw in the opening here that 1 over n squared by the sequence of partial sums converged, shouldn't 1 over n squared plus n also converge? Yeah, it should. And it does. Okay? Now, it's knowing that it's convergent is one thing. If you are asked to find the sum, then that is going to be a trigger that, it has to be either geometric or telescopic. Is that geometric? Does that look exponential? No. So the only other thing it could be is telescopic. But telescopic, you can't expand it like a telescope unless you have it written something like this. Something minus something. So, man, I wonder if there's a way to decompose this single fraction into the difference of two partial fractions. Heaviside cover-up method. We get to reuse that. Partial fraction decomposition. So it's going to be something over n and something over n plus 1. All right, so here we go. What makes n 0 when you plug it in for n? 0. So cover it up and plug in the 0 to what's left. You get 1 over 1. So that is now the new numerator of the one you covered up. Negative 1 makes n plus 1 0. Covered up, plug in a negative 1. You get 1 over negative 1, which is negative 1. So there is the decomposition. Now it has that good old telescopic feel, don't it? So now you can start expanding it out. You get 1 over 1, which is 1, minus 1/2, plus 1 over 2 minus 1/3, plus 1 over 3 minus 1/4, plus ... The 1/2s cancel, the 1/3s cancel, the 1/4s will cancel. This one converges to 1. So it does converge. We anticipated it would, but now we can do one better. We can actually find the sum of the infinite series. So maybe you're not too shocked yet that we can have a finite sum for infinitely many terms. It makes sense. Let's look at this. Here's something that's easy to visualize. Let's say I have a Sacagawea coin. Yeah, Sacagawea coin. There it is. If I take one Sacagawea coin plus another half of a Sacagawea coin plus another half of a half, what's half of a half? A fourth. And then to that I add another half of a fourth, which is an eighth. And then to that sum I add another half of an eighth, which is a 16th. And then to that I add another half of a 16th, which is a 32nd. And then to that I add another half of a 32nd, which is a 64th. As I keep doing that, I'm going to keep adding something forever and ever, right? Plus 1/28, plus 1 over 256, forever and ever and ever. The terms are going to 0, but does the sum converge? Yeah, you can clearly see here that as I keep adding half of what's left, I'm getting closer and closer and closer to adding that last little piece of the Sacagawea coin, which means this sum should be approaching what? If this is $1 and that's going to end up be approaching the other dollar, $1 plus another dollar, this sum approaches 2. Infinitely many terms, because you can keep taking half, never going to get there, but the sum approaches 2. Okay, so there's a nice little example of another infinite sum that approaches a finite number. All right, how about this guy? Nth term test says what? Bless you. 1 over n squared goes to 0. Therefore, this thing has a chance at converging. Based upon our past experience, does 1 over n squared go to 0 fast enough for the sum to converge? Yes, it did for the integral. This was the P series for the integral, and it's going to be the same case for the sum. Okay? This will converge. So you might say converges. Great. But what if it says what is the actual sum? Now you're like, oh boy. Yeah, it has to be either geometric or telescopic. Is this geometric? No, so it's telescopic. But in order to get the telescoping action, I have to write it like part A. So what do I need to do here? I got to factor it first, which is 1 over n plus 3, n plus 1. And then guess what we're going to do from there? Now we're going to decompose it, and then we'll expand it out. So I'm not going to finish that one, but there's the evolution. They get less and less pretty, right? The first one was perfectly telescopic. The second one was factored, but we had to split it up. This one was expanded, so we have to factor it first. So if you want to do the heavy side and expand, I think that one there does not cancel out after the first term. I think that one has one or two that are still left. But they do eventually cancel out. And if you're not sure, just keep listing more terms. The more terms you list, the more sure you are that things will cancel out. So again, this is not a BC topic. You still will have to know if these things converge or diverge, but in terms of finding their sum, you're not going to have to do that. So you're going to have to find the sum of infinite geometric series and known power series, which we'll get to later. So we have a few tests, right? We have the geometric series, the nth term test, which we always do first, and now, on the heels of what we just did, we are going to have the integral test and the p-series test. Okay? Let's do the integral test first, since it's listed first. The integral test is a test for convergence for an infinite series. All of these tests are going to be that. There are some qualifying things for the integral test to work, and here they are. If f, the function, is a decreasing, continuous, and positive function. Decreasing means that after some point, the terms get smaller and smaller. It doesn't have to be monotonic decreasing forever. It just, after some point, the terms have to get smaller and smaller. The function f has to be continuous, and it can't be 0 or negative. So decreasing, continuous, and positive. How do you remember that? When dogs go to prison, they don't like it. What do? They cuss, naturally. Dogs cuss in prison. It's a known fact. Dogs cuss in prison. Huh? Dogs, dirty dogs cuss in prison. Yeah. A guy who is an email contact me who teaches another BC class said his kids remember DCP by PCD. Pre-cal doesn't help. Pre-cal doesn't help. And I don't know if I like that because there is no H, and I think pre-cal does kind of help. But anyway, however you want to remember it, I like dogs cussing in prison. I like to see an incarcerated canine going. So anyway, so if you have a function f of x that is continuous, positive, and decreasing, then the series and the integral from 1 to infinity of the same function, a sub n is going to be the same function as f of x. It's just a function of n instead of x. They are going to have the exact same behavior. They either both converge or they both diverge. So how is that helpful to us? Well, we know already from improper integrals how to evaluate improper integrals. So if we have then a series whose rule of sequence looks like something we know how to find the antiderivative of, then I can find the value of the integral from 1 to infinity. And if that diverges, then the series diverges as well. If the integral converges, then the series converges as well. So it is a two-way test, right? But it's all dependent upon the result of the improper integral. Okay, now here is an important thing. If we evaluate the improper integral and it's a finite number, then we know the integral converges and so does the series. But it doesn't mean then that the series converges to the same number, right? It's an entirely different thing. This is finding area and this is just finding y-value sums. Okay? The function also need not be decreasing forever, just beyond a certain point. There is also another nice thing about the integral test. It has something called the integral remainder. And the remainder is a really important idea. There are two remainders that you're going to be responsible for. The alternating series remainder, which we'll get to, and the last thing we talk about this year is the Lagrange error. The integral remainder is not part of the BC exam, but I like to talk about it. Okay? And what it tells you is, okay, if the series converges, you want to know maybe to what it converges. Well, it's not a geometric series, so you can't find the actual sum. It's not going to be telescopic because you can't find the actual sum. But let's say you add up the first n terms. Let's say it's 6. I add up the first 6 terms in the series, which I know converges. If I add up the first 6 terms, how close is that partial sum to the actual sum? Well, we call that the remainder. It's a safe upper bound. It's not the actual remainder, because if we were able to find the actual remainder from a partial sum, we would add them together and get the actual sum. So what it does is it gives us a safe upper bound. And we know then that if I add up the first n terms, I'm going to be within a certain margin of the actual answer. Does that make sense? So if I add up the first 6 terms, then the remainder tells me maybe I'm within a tenth of the actual answer. Okay? No more than a tenth. It could be anything less than a tenth. And the way we find that with the integral test is it's just the integral. If you add up the first n terms in the series, then the remainder is going to be less than or equal to that same number that you added up to infinity of the integral. And I'll show you how that works. It's pretty neat. Example 11. Let's just see it in action. It's the best way to kind of get a feel for it. Determine whether the following series converge or diverge. If they converge, find an interval in which the actual sum could live using a partial sum of 4. Okay, first things first, nth term test for divergence. What is the limit as n goes to infinity of n over n squared plus 1? 0, okay? So the terms do go to 0. So what does that mean in terms of the series? It has a possibility of converging, but not for sure. What does your intuition tell you? That it does? That it doesn't. Why do you say that your intuition tells you it does? I don't know if you can analyze your intuition. That's kind of counterintuitive. Right. If you get rid of the plus 1 and you simplify n over n squared, it's essentially 1 over n. So it's growing similar to 1 over n, which we saw in the very beginning by the sum of the partial, the sequence of the partial sums diverged. This one is going to have the same behavior. Okay. There's something called a comparison test later on that will lock that in. But your intuition can take you a long way for these types of problems. If it grows like 1 over n, it's going to diverge, just like the integral 1 over x diverged. So let's see. How can I tell? Well, if that were an x and that were an x squared plus 1, and instead of the series from 1 to infinity, what if I integrated it from 1 to infinity? Is that an improper integral that we know how to evaluate? Yes. Okay, so if you replace the n's with x's and you integrate from 1 to infinity, if this is something you know how to integrate, it's going to work. Now, do dogs cuss in prison? Is this function going to be decreasing beyond a certain point? Yes. Okay, is it a continuous function? Yes. Is it prison? Is it positive? We're starting at n equals 1. Is x over x squared plus 1 positive for all values of x greater than 1? Yeah, it is. So dogs cuss in prison, it's going to work. So let's go ahead and find the antiderivative. Your inside function is x squared plus 1. Its derivative is 2x. We get the x in the top. We're off by a 2, so we have a correction of 1/2. What's the rule of integration when your inside function is in the denominator to the first? Natural log. So it's the natural log of the absolute value of x squared plus 1. And we evaluate it from 1 to infinity. Remember, if this is a free response, that has to come from a limiting process. So you would want to do this. You would want to do the limit as b goes to infinity of b. Okay? So now when I plug it in, and I'll go ahead and do that here, I get 1/2 the natural log of b squared plus 1 minus the natural log of 2. And I'll leave the 1/2 out front. Now, when I plug in, what is the limit as b goes to infinity of the natural log of b squared plus 1? It's essentially the natural log of infinity, right? And what is the natural log of infinity? It's infinity, right? If you hop on the graph of natural log and you head out to the right, it goes up forever and ever. Not very fast, but forever and ever it goes up. So this is infinity minus a finite number, which is what? Infinity, okay? So the integral diverges. And what does that mean then for the series? Yeah, so the integral diverges, comma, so the series does too, T-O-O. They have the same behavior, okay? Now, is there any point in trying to figure out what the partial sum is and how close it is to the actual sum? Not if it diverges. Yeah, not if it diverges. All right, this one here. Nth term test says goes to 0, has a shot at converging. What does your intuition tell you? Yes, the plus 1 is really meaningless. It grows like a 1 over n squared, which we already saw is a convergent thing. So this one we're going to be able to discern from intuition, but to prove it, you can't say intuition. All right? We're going to have to do it a different way. Is 1 over n squared plus 1 something we could integrate with respect to n? Or 1 over x squared plus 1 with respect to x? Yes. Yeah, so let's write it. The integral from 1 to infinity of 1 over x squared plus 1 dx is something we know how to integrate. Do dogs cuss in prison? Is it decreasing? Yeah, the denominator is getting bigger faster than the numerator. Is it continuous? Yeah, for all values of 1 to the right, it's continuous. Is it positive for all values bigger than 1? Yeah, so precalc don't help. Dog. What is the antiderivative of 1 over x squared plus 1? Arctangent. Good. So this is arctangent of x. And I'm going to go ahead and do it multiple choice style, okay? MC style. Which maybe your intuition would be all you need, right? Yeah, we're starting at 1 on the series to infinity, so 1 to infinity. So we get arctangent of infinity, wink, wink, minus arctangent of 1. What is arctangent of infinity? Pi halves. Good. Right? It has the horizontal asymptote. So as you go to the right, it approaches pi halves. If you go out to the left, it approaches negative pi halves. And what is arctangent of 1? Pi fourths. Now, it doesn't really matter. This right here is finite. Yes? So the integral and the series, what? Yeah, converge. Do they both converge to pi halves minus pi fourths? Heck no. Only the integral converges to that number. The series converges to something else, more than likely. So now we can figure out what the interval is and where the series must live. So here's how we're going to do this. We're going to do it with the help of a calculator. We want to figure out what the sum of the first 4 terms is. So S of 4. Now it's up to you if you want to do it by hand, manually typing them in, or if you want to use the sigma. Let's use the sigma. Alpha window number 2. I'm going to cruise from x equals 1. And again, your calculator knows that that's going to be a positive integer to 4 of 1 over x squared plus 1. And again, back in the day, this type of calculation, although it might be a little tedious, was not that difficult to find by hand. So the sum of the first 4 terms is 0.858. Okay? Now, because this is dogs cussing in prison, we know that every term that comes after it will be smaller than the previous term and also positive, right? So the actual sum, the true sum, which we now know converges, is going to be what in relation to this number? Bigger, right? The question is, how much bigger? We don't know what the actual sum is, but there is a way to figure out an upper bound for how far within the actual sum this number lives. And here's how we find it. If you add up the first 4 terms, then the remainder, using 4 terms, is going to be the integral from 4 to infinity of 1 over x squared plus 1. That's how you find it. If you add up the first 4 terms, you just integrate from 4 to infinity. If you add up the first 10 terms, then you integrate from 10 to infinity. Pretty nice. Now, we already know the answer to this, kind of. It's going to be arctangent of infinity minus arctangent of 4. What is arctangent of infinity? Pi halves. Now, pi halves minus arctangent of 4. We don't really know what 4 the ratio is from the unit circle. So let's do this. I'm going to store this as alpha A. And now I'm going to type in pi halves. I'll just say minus arctangent, which of course is second tangent of 4. And I get that. I'm going to store that as alpha B. And I'll go ahead and write that down, 0.244. So what this means then is if I add up the first 4 terms in that particular series, I know my actual sum is going to be no more than 0.244 units bigger than what I have. It could be less than that. It could just be 0.1 bigger, but it's not going to be any bigger than that. So it doesn't give us the actual remainder. It gives us a safe upper bound. So here we go. The actual interval then in which the sum lives. S is the actual sum. It's going to be contained between what I stored as A, which was this. That's a good lower bound, right? And then upper bound would be A plus B. So very quickly in the few minutes that remain, it's going to be between 0.858, and then if I add the remainder to what I stored as A, I get a safe upper bound 1.0103. Okay, cool. And that's pretty nice. That's about the best we can do without finding the actual sum. Now you could actually kind of home in on the sum by using the summation command on your calculator. If you want to find the actual sum from 1 to 1,000 or 2,000, I guarantee it's going to fall in between those two numbers. Okay? They didn't have that luxury back in the day. They didn't have these computers that could do routine calculations very, very quickly. Okay? So in this case, there was a trade-off, right? The fewer terms you used, the easier it was to find the sum, but the larger the margin of error was. Okay? You'd have a larger window here. So it kind of has something to do with statistics like confidence intervals and margin of errors. Your interval is larger if you use fewer terms. If you use more terms, your interval is smaller, but it's a lot more tedious. So anyway, I think you're getting a good taste of infinite series. They're kind of fun, kind of different. We'll pick up with example 12 tomorrow and maybe try to move a little bit more quickly. I doubt we'll finish this section tomorrow, but I'm going to do my best. So have a great rest of the day.